For 2 centuries, industrial progress operated on a simple, unforgiving equation. To extract more economic value, we had to consume more of the earth. From the first steam engines to the expansion of rail, every leap in physical output demanded a corresponding spike in resource extraction. The environmental cost was treated as a deferred debt. Even as assembly lines digitized and computers arrived to automate production, that underlying math remained intact. Industry simply began consuming vast amounts of electricity and silicon alongside coal and steel. Today, we have reached the physical limits of that model. Carbon emissions and severe water stress are no longer abstract concerns for future generations. They are strict, legally binding constraints written into global trade agreements. The old ledger, trading planetary health for economic growth, cannot be sustained. Heavy industry must decouple physical output from environmental waste to survive the coming decades. Artificial intelligence offers the first viable mechanism to break that historical constraint. It is a general-purpose technology capable of optimizing thousands of variables at once, tuning the physical plant in real time. This chart shows the projected economic impact of that optimization. Looking at the manufacturing column on the far left, McKinsey estimates AI could add a UK-sized economy to global GDP every single year. AI functions as a real-time optimization system, allowing industry to improve the industrial balance sheet without extracting additional resources from the ground. This graphic outlines a massive hidden drain on that balance sheet: unplanned downtime. Emergency machine stoppages cost the world's largest companies roughly $1.4 trillion annually. This diagram maps the evolution of asset management. In the past, managers relied on reactive repair or calendar-based preventative maintenance. Modern solutions use predictive analytics, reading live thermal data to foresee failures, then become prescriptive, calculating loads to recommend exact interventions. Returning to the data, we see the real-world results of this shift: a 70% drop in catastrophic machine breakdowns and a 25% leap in overall equipment effectiveness. Stopping a blast furnace failure protects margins, while simultaneously eliminating the emergency part shipping, energy spikes, and carbon output required to restart a cold plant. But the intelligence optimizing the factory floor is itself a machine, one with an absolutely massive appetite for electricity. This graphic breaks down the environmental toll. By 2030, data center electricity demand will double, surpassing Japan's consumption. Deploying AI without strict energy accounting doesn't solve emissions. It simply relocates the environmental damage from the steel mill to the power grid. Raw processing power is a liability if its carbon footprint cancels out its industrial savings. Balancing this ledger demands a rigid system of governance. This chart visualizes the accompanying labor transition. While the World Economic Forum projects a net global gain in jobs, the disruption to individual workers in legacy industrial corridors remains immediate and severe. This visual outlines the doctrine of augmentation, not substitution. AI acts as a supportive overlay to process vast datasets, but a named human engineer must retain ultimate accountability, questioning assumptions and owning the consequences of all critical safety decisions. True resilience in heavy industry does not come from a flawless mathematical model. It is built on human judgment, armed with perfect, real-time data. This architecture diagram outlines the required legal framework. At the center is data sovereignty, governing worker information under strict privacy laws. Furthermore, AI must be secured through cybersecurity by design, while policies ensure equitable diffusion so smaller businesses can access the same advanced tools. Professor Kapilaswar Mishra's final mandate redefines industrial success as producing better, leveraging intelligence to secure greater value for society with fewer resources and less waste. Sustainable value requires this shift in engineering discipline. This is the pursuit of intelligence without waste.